Well, welcome back, folks. Well, you knew it was coming eventually. It's time to touch base with one of many students' least favorite topics. It's the trig functions. Now, before anybody starts to get terribly upset, don't worry. This is actually not as bad as some people like to make it. So let's see what we can do about getting started. Number one, there will definitely be involved some memorization, but we're going to kind of logic it out to begin with. And the first thing we're going to do is we're going to look at the graph of a sine function. Now, what I've got here is the graph of a sine function, and you can notice that I've highlighted a few critical points. And I'm going to say that I'm even going to give you what the slope is at each of these points. For example, at negative pi, I've got a slope of negative 1. At pi over 2, or negative pi over 2, I have a slope of 0. At 0, I have a slope of 1, and at pi over 2, I have a slope of 0, and at pi, I have a slope of negative 1. Next thing I'm going to do is I'm going to make a graph of these slopes. So there's my slope, got it, okay, and I'm just going to draw in each of my points here. You probably can't see these buttons really closely because the dots are very small, but here I'm going to connect the dots so you guys can see. And let's do that. Connect the dots. And what do you notice? Hoping you guys are recognizing that shape as being the graph of a cosine curve. So therefore, when we're talking about the derivative of sine, we're going to say that it is cosine x. Now, there are going to be one or two of you that are going to be kind of, well, mathy, and they're going to say, well, that's intuitively making sense, but is there any way of proving this using algebra? And I'm going to say, yes, there is. Again, please understand that if you were taking a Calc 1 class at college, this would be one of the things you would have to do for this chapter is actually go through and mathematically prove that the derivative of sine is equal to cosine, and you would have to use the f of x plus h definition. So the first thing I'm going to do is I'm going to pull up my f of x plus h definition, and I'm going to substitute in values. And the next thing I'm going to do is I'm going to use something that you haven't seen in probably close to a year at this point, which is the sum of sines formula. For those of you who've managed to forget it, there it is. And what I'm going to apply it to is going to be to this portion right in here. So sorry to disappoint you on that. That's how I'm going to apply it. And so let's see what we can do about cleaning that up. And let's see where we can go there. Okay, so next, when I apply the sum of sines formula, I get this. Now, next thing I'm going to do is I am going to talk about combining together some terms that I can kind of group together. I'm going to group this one here with this one here. I'm just going to shift things over, and then I'm going to factor out a GCF of that. So let's do that here. And there we go. Now I've factored that out, and I'm now left with this expression. Again, for those of you that are having some issues with this, please note this has just been moved down here, and this in here has been grouped together, and I just factored out sine x, and that's how I got down to this line. Now the next thing I'm going to do is I'm going to apply I'm going to apply the limit to pieces inside. So watch how I do this. I've got the limit as h approaches 0 of the sine of x times the limit as h approaches 0 of this second part in here, like this. And then I'm going to say plus the limit as h approaches 0 of that part in there. Well, what happens is now I substitute in h of 0, and, well, let's be honest, all that happens now is I kind of clean things up, and I have that the sine of x times 0, because, again, this is one of those identities that you were asked to memorize way back in chapter 2 or something. Anyway, you get the idea. So we've got that there. And the next thing I can do is I'm also going to sub in 0. And oh, wait, that's just going to get me 1 because I know that the limit as h approaches 0 of this is also going to be 1. Okay, so back into that. And so the sine of x times 0 is just, well, 0. And then I add to that the cosine of x, and congratulations, you've proven that the derivative of sine x is cosine x. Now, once again, you will never need to do this for my class or for the AP test. But in a traditional Calc 1 class, that would be one of the questions on the test for this chapter. Either that or you'll have to do the same thing for cosine. But I'm really hoping at this point everybody just recognizes that the derivative of sine is cosine. Just have that memorized. Now let's take a look at the next one here. Sorry, we'll do this. And we'll go with that. And got it. Next, we're going to do the same thing for the cosine function. And notice I'm determining my slope here to be 0, my slope here to be 1, my slope here to be 0 again, my slope here to be -1, and my slope at this point is going to be 0. And once again, I'm going to connect the dots on that. And once again, that looks familiar, but it's not just sine. Looks like it's the sine function that's been, well, flipped over the x-axis. So we're going to just describe it as a sine curve that has been reflected about the x-axis. And how do we go about getting that? Oh, we just put a negative out in front of it, and that's a reflection across the x-axis. So once again, this is something that we can memorize. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, I can memorize that, and I'm good. Now, believe it or not, if I really wanted to be super lazy about memorizing stuff and I'm really mathy, I could stop at this point because guess what? I can actually use those two derivatives to, well, find the rest of the trig derivatives. For example, right now we're going to talk about the derivative of tangent. Now, we can memorize. As a matter of fact, we probably will memorize. But if you get stuck and you've forgotten what the derivative of tangent is, what can you do? Well, using stuff that you learned last year or the year before, you take tangent, which is the same thing as sine over cosine. And then the derivative of sine over cosine, wait a second, that's going to be quotient rule. So I'm going to say low d high minus high d low. And yes, we're just using those derivatives that we just got done getting comfortable with to apply to this. And now we're going to try and combine some stuff together and say, oh, look, it's cosine squared plus sine squared, which even if you struggled a bit with trig, you're probably still going to remember that that one is going to be equal to 1. So I'm now looking at 1 over cosine. Well, 1 over cosine squared. And what is 1 over cosine? Why, that is secant. So I can say that the derivative of tangent of x is just going to be secant squared x. Okay. And I would ask for questions at this point, except, well, we're not live, so we can't. Next up, let's see what we've got here next. Okay, just have that function in there. Hoping that that is going well. Again, feel free to pause this if you need more time to write stuff down. Do you need to be able to do this? No, we're just going to say that you're going to memorize it probably, but there's a reason where things come from where they come from. All right, next up, there are other trig derivatives, and I could go through the process of doing this, but my guess is most of you would probably say, I'd rather not. I'd rather just have them and memorize them. And now you're going to look and you're going to say, well, the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant. And then we've got secant and cosecant. Boy, if I didn't know better, I'd say there was some things here. There was a pattern that I could somehow talk about. Let me see if I can write something over off to the side and see if that helps people at all. So we go d dx of sine x is cosine. And d dx of cosine is negative sine. Okay, now Is there a common thread? Watch. I'm saying that I've got tangent and cotangent there. Okay. Let's see. Tangent and cotangent. They get me secant and cosecant. That seems to kind of be close. Let me see what else I can do here. How about I take a look at secant here and cosecant? Secant gets me secant tangent, and cosecant gets me cosecant cotangent. Hmm. Hmm, 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 hmm. Well, let's see if there's something else I can do. And I'm looking at one is sine and one is cosine. I'm hoping that some of you at this point are pretty much screaming at your computer screens going, Johnston, it's just the co stuff. And I'd say, what? Notice, this is tangent, this is cotangent. This is secant, this is cosecant. Here's sine, and here's cosine. Once again, I'm hoping that people are like, yes, that makes perfect sense. We're very cool on this. Well, but there's going to be people that are not going to be so cool on this. Well, what can we do? In reality, all I really need to do on this is memorize this top shelf in here. So let's do it in, say, purple. All right, well, that didn't come out purple, but you get the idea. And what is happening? Anytime I've got a co, I could have a negative. I've got a co, I've got a negative. I've got a co, I've got a negative. And if you've got your original, you should be able to come up with the rest on your own because they follow the same pattern. Secant squared becomes negative cosecant squared. Secant tangent becomes negative cosecant cotangent. And cosine just becomes negative sine. So that pattern should hold true and should make your life a little bit easier. All right, then. Well, let's see what else we can do on this. How about we take a look at this? The third derivative of position is called the jerk. We really don't use it like ever, but the physics people would probably cast me in front of a pile of burning coals if I didn't at least mention this word once. But if you hear it, don't get bedazzled by that. The last thing I'm going to talk about is taking multiple derivatives of something. Now, I could spend a copious amount of time talking about this, but what I'd really like to do instead is just show you real quickly exactly what we've got. You remember that when you were doing powers of I to the first got me I to the second was -1, I to the third was -I, and I to the fourth was, well, I squared times I squared, which is 1. And then you started saying, well, what's I to the fifth? Well, I take 1 times another I, which is going to get me I to the fifth, or I to the fourth times I, which is, well, just going to be I again. And what ends up happening is this pattern just repeats itself over and over and over ad infinitum. Now, as it turns out, we've got the same sort of thing going on with sine and cosine. So watch carefully. If I have, say, cosine, if I'm going to take the derivative of cosine, everybody's going to say, okay, that's negative sine. And if I take the derivative of negative sine, that's just going to be negative cosine. And then if I take the derivative of negative cosine, that's going to get me just plain sine. And then we finish up by saying, well, the derivative of that is going to get me back to where I started. And what happens is when you take the continual derivatives, guess what? This pattern repeats again for 5, 6, and 7, and 8 derivative, 9, 10, 11, and 12th derivatives. Don't worry for those of you that are like, I'm not 100% sure what he's talking about. This is part of the exit slip. It's problems 10 through 12. If you're still stuck on this, I would recommend asking me about it tomorrow in class. Other than that, sorry to disappoint you, but I'm going to have to say that at this point, I'm going to shut things down and call it quits. Good luck to you, one and all, and hope you have a lovely rest of your day.